In this video, we're going to generate code for a small example program. The program we'll take a look at takes a positive integer x and sums all the numbers from 0 up to x. So if x is 0, then the result is 0. Otherwise, it is x plus the sum of all the numbers up to x minus 1. So this isn't a very interesting program, but it does illustrate all of the features that we discussed in the previous couple of videos. So let's dive right in and talk about how we're going to generate code for sum2. So we begin by giving it a label for the entry point to the function. So that'll be the sum2 entry. All right, and now we have to generate code for the caller's side, callee side, excuse me, of the calling sequence. So what was that? So the first thing we have to do is we have to set up the frame pointer, which will just be the value of the stack pointer. So that's the frame pointer for this activation. And then we're going to have to store the return address at the current value of the stack pointer. And then we're going to move the stack pointer. And of course, whenever we store something on the stack, we have to move the stack pointer to the next unused location. All right. Okay. And so now we have to generate code for this if then else. All right. And the very first thing, if you go back and look at the code for if then else, is to generate code for the first sub-expression of the predicate. So we're going to generate code for x, and that's really easy. Remember, generating code for a variable just looks up the variable in the current position of the frame. Sorry, at the correct offset from the frame pointer. All right. All right, so once we do that, now we're generating code for the predicate. And how do we do that? Well, we've generated code for this first sub-expression, and now we have to save that sub-expression somewhere because we're going to generate code for another sub-expression. So the equality there is a binary operator, so we have to save the value we just computed somewhere on the stack. All right, so we'll do that. So we'll store the value of A0 on the stack. And that will involve, as always, moving the stack pointer. Okay. And now we generate code for the second sub-expression of the predicate. All right, and that's also easy. That's just a load immediate of the immediate value into the accumulator. All right. And now we're going to load the value that we saved for the first argument of the predicate back into a temporary register and actually do the comparison. So this is more code that's actually part of the conditional. All right. So we do a load word into T1 of the value that we saved before. Okay. And now we need to we need to pop the stack. Okay, so we'll do that here. All right, because we're done with that value. So we'll all right. And now we're going to do the branch. So now we test whether the two sub-expressions of the predicate are equal or not. And if they are, then we jump to the true branch. And here I'm going to give the true branch a unique label, because this might be part of a larger program where there are many if-then-else's, and so I'm going to append some identifying number on the end. Instead of writing out true branch, I'll just call this true 1. All right? Okay, and if we fall through, then we're on the false branch. We'll call that false 1. And now we're generating code for the false branch, which is this summation here. All right, and how are we going to do that? Well, this whole thing is a plus expression, which means we have to generate code first for the first sub-expression, which is just x. All right, so what do? Well, we load to generate code for x. We look up x at its current offset. At its appropriate offset in the frame using the frame pointer. Okay, it's the only argument, and so it's at 4 from the frame pointer. I'm sorry, the only argument to the procedure, and so that's stored at the first position for arguments, which is always at 4 from the frame pointer in our scheme. All right, and now that we've loaded it, we have to save it because it's part of a binary operation, so we're going to save that value on the stack. Okay, and now we will adjust the stack pointer. Okay, and what are we going to do next? Well, now we've computed this sub-expression, this x. All right, we can't do the plus yet until we compute the second sub-expression, which is the function call. All right, so now we have to generate code for the function call. And I'm going to move up here to the other side of the screen here to show the rest of the code. Okay, and the first thing we do to generate code for the function call is to start setting up our activation record. All right, this is setting up the new activation record for the function call we're about to make. All right, so what do we do there? We store the frame pointer. Okay, store our old frame pointer at the stack. Okay, on the stack. All right, and now we have to compute the argument. All right, we have to compute the x minus 1. So that code gets inserted here in the template for a function call. So what's going to happen there? Well, we're computing a subtraction. So the template for a subtraction is to first generate code for the first sub-expression, then generate code for the second sub-expression, and then subtract them. All right, so let's do that. So first we generate code for x again. Okay, and now since it's the first argument of a binary operation, we're going to save it on the stack. All right, now we generate code for the second argument of the subtraction. Okay, and now we perform the subtraction. So we have to load the first argument back into a temporary register. We have to actually do the subtraction. Excuse me here. All right. And now we can pop the temporary value off the stack. Okay, so now we've actually done the subtraction. And let me see, that is everything from about here down to here is computing x minus 1. Okay, and this was computing x, and this was computing 1, and then this whole thing is computing the subtraction. All right? So now we've computed the argument. What are we going to do? Well, we save it on the stack. So now we save the result on the stack. We're saving it into the new activation record that we're building. All right. And then we have to advance this, or move the stack pointer as always. And now we're ready to actually do the function call. So now we do the jump and link to the entry point of sum2. Okay, and now when this returns, what's it going to return with? It's going to return with the result of computing sum2 in the accumulator. All right, and so then we're ready to perform the addition, because now we've computed the second argument to the addition. And how do we do that? Well, look back at the template for addition. The next thing that happens is we reload the temporary value that we saved on the stack. All right, and now we can actually perform the addition. Okay, and then we can pop the temporary value off the stack. All right, and that actually ends the else branch, the false branch of the entire if then else. Okay, so now we branch around the rest of the if then else code, and we'll call that label end if one. And now comes the code for the true branch. And what are we going to put there? Well, it's not very complicated because all we're doing on the true branch is loading or generating code for 0, which is just a single load immediate. Load immediate. All right, and that's the entire true branch. And so now we're at, there should not be a colon there, excuse me. In fact, I can just erase that a little bit. All right, and now we're at, and actually I see I wrote this in the wrong place. So let's fix that. So this is a branch at the end of the false branch, at the end of the else part of the if, and we're going to branch around the code for the true branch, which is only one instruction. And so the very next instruction is the label end if. So now what's left to do, we've generated code for the whole if then else, and so now what goes here is the rest of the template for the function definition. So now we just have to generate the code that returns back to the caller. And how do we do that? Well, we have to load the return address from the stack. Okay, and now we pop the stack. So we pop the entire activation record off the stack. And how big is our activation record? Well, remember, there's always two words, one for the return address and one for the frame pointer, and then a number of words equal to the number of arguments. Well, there's only one argument here, so we have 3 words, so that's 12 bytes. So we increment the stack pointer by 12. All right, and then we load the old frame pointer, we store the frame pointer. Okay, and then we return. So one more instruction. You do a jump register to the return address. And that is the entire code for this simple function sum2. And there's a couple things to point out. So first of all, the code is constructed as a bunch of templates pasted together, and I tried to point out as we go along how that works. But you do wind up with one linear sequence of code. All right, and if you're at all confused, it's be worth it to go back and look at those templates and look at this example and understand how the code all fits together and how it works. And the other thing I would point out is just that this is extremely inefficient code. So like over here, where we were generating code to check whether x is equal to 0, notice here that we load x. So this is a load of x. And then we immediately store the x again into the stack. So we just loaded it from the frame, then we immediately store it back into memory. And then we load an immediate value, and then we reload the value of x here. So moving the value of x, we all around. So we load it, we store it, we load it again. And so there's a lot of wasted motion here. And that's a result of this very simple code generation strategy where we want to be able to compose code together, but be able to compose these templates in a way that will work properly. Code does not have to be this inefficient, and a lot of the techniques that we'll discuss in subsequent lectures, we'll talk about smarter code generation techniques and also optimizations that can even improve the code further.